This is 388 Lab 10, Semiconductor Light Sources by Ryan and Corey. So for this first experiment, we were exploring physical properties of the laser diode and LED, which we observed using this microscope and a camera hookup. This is the LD lasing at low intensity, which is a little out of focus because the casing got in the way. But here we have a close-up of that diode without the casing, and here's the side. We measured this black box, which is the laser cavity. We also looked at a white LED, which is composed of a red, a green, and a blue emission area, each individually driven by current. You can see those here, lasing individually. And we calculated those individual emission areas. You can see them here. They're each about 0.7 millimeters squared overall. And that aligns with the typical specifications for an LED, which are usually around 1 millimeter squared. Using the length of the laser cavity that we measured as 0.7 millimeters, we were able to calculate the longitudinal mode spacing. And it seems like we over-measured the length of our laser cavity a little bit. We're a little outside of the typical range, which resulted in a lower longitudinal mode spacing than is typical.
For experiment B, we used a Thorlabs OSA to measure the output spectrum of the LED versus drive current. We observed this at 3 currents, one below, one at, and one above threshold. We measured the mode spacing on these graphs by taking the distance between peaks on our spectrum, as you can see here. As we increased current, the output spectrum became more distinct, as you can see in this video. We found our node spacing to be 0.155 nanometers. Comparing this to part A, we found an error percentage of 47.4%. This is very high, but it's most likely due to the measurement of a large laser cavity length. We also have the expected LED spectrum for our light right here. This matches well with our observed emission spectrum with one monochromatic peak in the red wavelengths area.
Experiment C focused on measuring beam divergence and polarization characteristics of the LED and laser diode. We used the square wave and rotated the light source to observe voltage as a function of rotation on the oscilloscope. The beam divergence of the LED is shown here. As you can see, it falls off faster at higher angles with almost no power above 60 degrees. This matches the typical LED spec shown at the right. Additionally, we added a linear polarizer to the resistor and found maximum and minimum transmission, which we used to calculate the polarization ratio, which was close to 1, indicating that the LED is largely unpolarized. We repeated this experiment with the laser diode in 2 orientations, with the broadband horizontally and vertically aligned. These graphs are seen here. As you can see, the divergence occurs over a much shorter angular region than for the LED. Again, we found the polarization ratio, which was 2, indicating that the LD is significantly polarized and certainly more highly polarized than the LED.
Finally, for part D, we used an integrating sphere to measure the output power versus drive current for both an LED and an LD. We took these values for a drive current from 0 to 40 milliamps, and we were able to make the following graphs from our data. As the graphs imply, after the LED reaches threshold current, it begins to increase at a much higher rate, while the LED increases at a near constant rate.
It's important to be able to measure and characterize these different light sources because they have various applications within optical systems.
See you next week.